All right, I posted the video from last time on YouTube. I don't know if you checked it out. I already got one comment from some like girl in her underwear saying she wants me to be her boyfriend. This is a bot, I'm pretty sure. This is a bot. Feel free to leave a comment. Not like that, please. Yeah, they are. I'm going to put a link on our class website to where all the videos are so that you can see them. Although hopefully, you know, tune in live and you won't have to check them out. But you can always look at them if you feel like you missed something or you just want to see it again. So last time around, I sort of finished off by talking about some properties of the real numbers. So the real numbers are, I hope you don't mind me sitting here on this table. I'm not sure. Oops. I don't think I can do this while I'm standing up. Maybe I'll try. But then I got my papers here. It's all so new to me. R is an ordered, this is what I said at the very end last time, ordered field. So a field, like I said, is it refers to a set of things which can be added and multiplied, and they have additive inverses and also multiplicative inverses. So this is like a group if you're familiar with the abstract algebra, but a group just has one operation. A field has the two operations, and they have some properties which we don't really need to get into. And it's also ordered. That is, the real numbers have a particular ordering to them. They live on the real number line, and they have an order. All right. There are many different ordered fields, though. Like, for example, the rational numbers, the set of rational numbers is also an ordered field. You can add and multiply rational numbers. They also have an ordering to them. But what's the difference between R and the rational numbers, which we write as Q, is that R is also complete. This is the sort of technical word that we're going to talk about. This is like our first big topic, is called the completeness property of the real numbers. I don't know actually if I'm going to get to saying fully what the completeness property means, but basically I would say, intuitively speaking, I would say what this means is that R has no gaps in it. If you think you live in a universe with only rational numbers, if you look closely enough, particularly in geometry, you will discover, like the Greeks did, that there are some numbers which are not rational, even though they kind of look like they represent some kind of lengths geometrically. They somehow fall in between the rational numbers. What I'm saying is, in the set of rational numbers, there's a bunch of like empty things. There are things in between the rationals which are not rationals. That's what I would call like gaps in the set of rational numbers. But the real numbers is not that way. The real numbers kind of already includes any possible number that you could think of. There are no other things like in between the real numbers. Now, you probably heard of imaginary numbers. They don't really live in between the real numbers. They live sort of outside of the real numbers. So don't think too hard about that. So this business about gaps is what we are going to talk about. Most of what we're going to say about the gaps between the rationals and such is going to have to do with very small numbers. So I'll say pay attention to very small numbers. You know, something I said last time was that one of the major concepts of this class is going to be making sense of what exactly limits means. And limits, whatever you think about them, they do have to do some, they have to do in some way with very small quantities, or like things which get very close to one another, right? These have to do with, I'll say, very small, oh sorry, when I wave this around I'm going to do this. There we go. Now I can do that. All right. We're going to pay attention to very small numbers, which have a lot to sort of figure in when we talk about limits. And in particular, small distances between numbers. So let's start talking just about distances between numbers. This is easy enough. Go to a new, oh no, I want to go to a new page. I thought that was easy. I'll do it. I'll do this. small distances between numbers. Sorry, you can't see that anymore. Small distances. Maybe I'll just do it like that. So let's talk about distance between two real numbers. Everything I'm going to say for the next 20 minutes or so I think will be very simple. Distances between two numbers. So for distances, we use absolute values. For example, the distance between two numbers, x and y. Can anybody tell me, how do you write the distance from x to y in terms of absolute value of something or other? Can you write that in terms of the absolute value? Yeah. Yeah, the absolute value of y minus x, which is the same as the absolute value of x minus y. Would you mind? I was going to write it this way. The absolute value of x minus y. That's the same as the absolute value of y minus x, of course. The distance between x and y is the absolute value of x minus y. Because the distance among real numbers is defined in terms of the absolute value, we're actually going to be using absolute values a lot in this class, probably more than in your other classes. Unfortunately, like in a calculus class, or I remember for myself when I was in high school, say, my approach to absolute values, when I had to deal with absolute values in equations, my general approach was I am going to just ignore the absolute values because that always made things easier. Although it's often wrong, and in this class especially, we are actually really going to have to deal with absolute values and not ignore them, unfortunately. This will be kind of taxing from time to time, but it's all right. We can handle it. So one major important property about absolute values that we're going to use all the time. So this is a property of the absolute value, which I'm sure everybody knows. Absolute value obeys something called the triangle inequality. The triangle inequality, it says x plus y. The absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. The reason this is called the triangle inequality is because actually the phrase triangle inequality comes from the version of this which works for vectors. If you take the vector magnitude of a vector x plus y and related to the magnitude of x versus the magnitude of y, they look like this. If you have, say, x and y are two vectors, and the length of x and the length of y, the length of x plus y would be, if you imagined this right there, right? This is x plus y. If these were vectors, where this one over here is like another copy of y, what this says on the picture is the length of x plus y. Can you see that little guy? The length of x plus y is shorter than this length here plus this length here, right? That's why it's called the triangle inequality. It says that basically the straight line between 2 points is shorter than some other two segments to get to the same place, right? So it's called the triangle inequality. In terms of real numbers, it looks like this. And there isn't really a triangular analogy, but this is like the one-dimensional version of what for vectors we call the triangle inequality. Anyway, we still call it the triangle inequality. All right. This is the most important property that we're going to use over and over again about the triangle inequality. Because absolute values describe distances, it is a fact. I'll write this as a theorem, although I don't think we need to talk about why this is true. This is sort of an obvious fact. X minus y equals 0. I'm going to say if and only if, and want to complete the sentence there. What can you say about x and y? If x minus y, the absolute value, is 0, what do you say? X equal y, right? I hope you agree with me that this is all kind of obvious. The only way the absolute value of x minus y can be 0 is if x equals y, right? You could easily write a proof of this if you wanted to. I don't think we need to get into that. I'm going to say something even better. This actually is not obvious, what I'm about to say. So a better version of this theorem is another way to tell when two numbers are equal. what I'm about to say should not seem like mind-blowing. It's probably something that you haven't seen before, but it's still kind of obvious. Anyway, here, I'll say it. This is extremely important, at least not the fact itself, but like the point of view behind the fact, or the approach to writing things in the way that I'm about to say is kind of the way of thinking about it is the same way that we're going to think about almost everything in this whole class. Here it is. It says, if I have two numbers, let's say A and B, in the real numbers, I hope you don't mind this little notation here. This little guy means they're in the set of real numbers. This is a little set theory for you. If A and B are real numbers, then A equals B, if and only if. I'm going to write IFF for if and only if. If and only if, here it is. For every epsilon greater than 0, absolute value A minus B is less than epsilon. All right, so this, whoa, I can do lightsabers. Look at that. Okay, this thing is called epsilon. This is a Greek letter, which we're going to use all the time in this class. The notation with the epsilon, I believe, goes all the way back to Weierstrass when he first wrote down these ideas about limits and such. Even though he wasn't exactly the first, he was the first that anybody really paid attention to. He used epsilon. This phrase right here, for every epsilon greater than 0, this is like if you wanted to, I don't know, if you wanted like a slogan from this class, we are going to say those words over and over again. And in fact, I hope to impress on you, there's real depth encoded in those words in a way that is hard to notice at first. But the more you sort of live with it, the more power you can see in those simple words. Anyway, this is what the theorem says. It says A equal B. That's one side, right? Yeah, I don't like the lightsaber. I'm going to go back to the dot. Okay, A equals B over here is the same. That's what the if and only if means. It means these two things are logically equivalent. If A equals B is the same as saying for every epsilon, that is any other number greater than 0, A minus B is less than epsilon, the absolute value of A minus B. You can think of that as the distance between A and B. Really what I'm saying here is the distance, if I were to interpret this sort of in words, this right there says the distance from A to B is less than, well, it's less than epsilon, but the thing that I circled in red says for every epsilon greater than 0. So really what I'm saying here is the distance from A to B is less than every positive number. Right? That's what we say. Now, do you agree that that requires, if that's really true, then A must be equal to B, right? If the distance from A to B is smaller than every number, then certainly they must be the same number, right? The distance, if it's smaller than everything, then the distance must really be 0, I guess, right? So that's why this is true. I want to actually do a proof of this because this is such a central idea. And this is really part of like Weierstrass's genius, or not just him, but all the other people who thought of this also. The principal problem with thinking of a definition for a limit is this bogus phrase like when x gets really, really close to 0 or something like that. Or the idea of thinking about some numbers are really, really, really small and some numbers aren't. That doesn't really mean anything. The genius of this little phrase here, for every epsilon greater than 0, it says this distance is smaller than every number, right? This is only interesting when you think of this epsilon as being a very small number, right? If we think of epsilon as being a very small number, what this says is this distance is like super duper small. It's like as small as possible, or it's smaller than anything you can think of, that small. Even though nothing in the statement of the theorem says epsilon is small, right? But the statement really is only interesting when epsilon is small. And in fact, when you say this, in some sense, it like requires you to think of epsilon as if it were being small, even though you didn't actually say that in the logic of what you're saying here. So this little phrase, for every epsilon greater than 0, is the way that you say something is really, really small without saying it, right? But that is really what we're talking about. It's strange. It's kind of an idea that you have to live with for a while before it really clicks. But anyway, I want to try and do a proof of this. So the proof. This is a if and only if. So we got to prove two things, right? If and only if means the first thing implies the second thing, and also the second thing implies the first thing. I think the first one is easier, so I'm going to do this direction first. If I think of this if and only if as like an arrow having two directions, you have to do each one separately. Let's do the first one first. So for this one, I assume A equal B, and then we need to show. So when I write a proof, I'm going to use these letters WTS for I want to show. It's always a good idea. I hope you learn this in your discrete math class, that when you're writing a proof, it's always a good idea to every so often restate what I'm about to demonstrate. What I want to show is really, this whole thing on the right side. Okay, so I want to show for all epsilon greater than 0, absolute value a minus b is less than epsilon. All right. I hope you don't mind. I'm using right here this little upside down capital A means for all. I hope you've seen that before. We're going to use this a lot in this class too, because every time you see this phrase for every epsilon greater than 0, usually I'll write it with the little for all. All right. Anybody think you can do this? So I have to do, if you want to show something is true for all epsilon greater than 0, I could say something like let epsilon greater than 0, and I want to show absolute value a minus b is less than epsilon. Anybody think you can do this? If you look at your assumptions, I think it's not so hard to connect the dots. What do you think? Yes. Somehow get it to where a equals b. Yeah, actually, in this part of the proof, we are assuming from the beginning that a equals b. So what can you do with that once you know a equals b?
It's a minus b to 0 epsilon.
Yeah, right. So since a equals b, we already know that a minus b equals 0. And so what I want to show, this a minus b less than epsilon, just like substitute in there, right? So I want to show that WTS. I want to show that 0 is less than epsilon. Look at that wiggly 0, right? What I want to show is that 0 is less than epsilon because absolute value a minus b really is 0. But this is part of our assumption, right? We always assumed all along that epsilon was greater than 0. And so this is certainly true. So this is, let me just say, this is true since epsilon was assumed to be greater than 0. All right? So that's that part. This is actually the less interesting part, or the easier part. I don't know if that seemed easy. Once you realize that a equals b is one of your assumptions, and then everything else just sort of follows automatically. I'm going to try to write with better handwriting too. I'm not used to holding the thing in this way. All right, the other way around. So this is the other part of the proof, which is more interesting, I think. In this case, we assume that other stuff is true with the epsilons. So here we assume that for all epsilon greater than 0, absolute value a minus b less than epsilon. And then we want to show that a equals b, right? This is what we have to do. So the distance from a to b, that is absolute value a minus b, is smaller than any number, all right? And you have to show that means a must equal b, okay? This one is most convenient to prove by contradiction. So I'm trying to give you this is an important proof, but also I want to do a little review of all your favorite proof techniques, because we are going to be writing a fair amount of proofs in this class. let's do a proof by contradiction. So I'm going to say, like most of the time when I write a proof by contradiction, I'm going to write it this way. I'll say, for the sake of a contradiction, and actually I'm usually going to write f-soc like that. This means for the sake of a contradiction, we're going to assume the opposite of what we're trying to prove, which in this case would be A is not equal to B, all right? This little, for the sake of a contradiction, is a nice little preface so that the reader of the proof knows when I make this assumption, it's not because I think it's actually correct, it's because I'm trying to obtain a contradiction, which is why I make this assumption of the opposite of what I'm trying to show. All right? So if we assume A is not equal B, then eventually I want to say something about this, absolute value A minus B, right? So can we say something? If A is not equal to B, then what can be said about absolute value A minus B? Yeah. It's not 0, right? In fact, it's greater than 0. Yeah, because the absolute value cannot be negative. So if A is not equal to B, then absolute value A minus B is greater than 0. Yeah.
Why would it not be not?
Why would it? You said not too many times.
It says absolute value of x minus y equals 0 and 0.
Yes.
So then we're saying that A doesn't equal B.
Yeah.
Then would it be absolute value of A minus B doesn't equal 0?
Yes, you could say that. But then, since the absolute value is always positive, if it's not equal to 0, it must be greater than 0. Yeah. Yeah. So.
It's the same thing. Kind of.
Yes, for absolute values, because they're always positive. It's the same thing. Yeah. Yeah, I mean, I suppose I kind of skipped a step, maybe. You could say then absolute value A minus B is not equal to 0, and therefore absolute value A minus B is greater than 0. Yeah, that's a good point, though. Yep. Okay, then absolute value A minus B is greater than 0. Check it out. Here's a cute little trick to finish up. Actually, you can more or less immediately obtain the contradiction. Does anybody see? I don't want to tell it to you if you already see the cute little trick. You can immediately obtain your contradiction. We have assumed, our assumption up here is that A minus B is less than every positive number. So what's the, yeah?
Well, you said it's greater than epsilon, right? And it's less than, I'm sorry. And then in the then it's greater than, and we assume that for all real numbers, that epsilon is greater than 0.
Yeah, right. So it basically comes around to, this assumption works for every epsilon. So I'm going to say it like this. If we use epsilon equal this absolute value A minus B, then epsilon will be greater than 0 because we just said the absolute value of A minus B is greater than 0. But then our assumption is that A minus B is less than every such epsilon. Then by our assumption, we have absolute value A minus B less than absolute value A minus B, right? Where this here is the epsilon, right? The assumption says A minus B is less than epsilon, for no matter what epsilon is, for every number that's positive. And since A minus B we said was positive, we can use that for the epsilon, and we say A minus B is less than A minus B, and that's a contradiction, because it's not. I mean, if it were less than or equal, that would be fine, but not less than. So this is our contradiction. Oh, write it in black. Come on now. All right, this is a contradiction. And that'll do it. Right? The distance from A to B, if we say the distance from A to B is less than every number, then, well, I guess that means it's less than itself, and that's a contradiction, right? So, unless A actually equals B, then the distance from A to B is 0, which is not a contradiction with anything. All right? Excellent. So, this is, like I said, I wanted to do a nice sort of proof to warm up with. This is a not so obvious proof, although you probably could have come up with this. Also to demonstrate the way that we are going to think of super small quantities without actually saying anywhere that they are super small, right? This epsilon, we imagine it to be very small, even though really all we said was just that this is true for every positive number, all right? It's kind of the quantifier, you know, these things, these and this, these are called the quantifiers. This for all quantifier, the universal quantifier, is really doing the work of talking about really small things all by itself. It's kind of logically magical to me. I don't know if that seems interesting to you. But. All right, let's continue on. Unless are there questions about that? This is a basic kind of epsilon style proof. We are going to write a lot of proofs which involve epsilon in exactly the same way, where epsilon is imagined to represent a very small distance, even though we never actually say it's very small. Okay, let's talk then about completeness. I said that completeness is the important property which distinguishes the real numbers from the rational numbers. And I said informally, completeness means that the real numbers have no gaps. Another informal way of saying this is something like, if we have a set of reals that somehow, like, let me say, sorry, I want to say this a little differently. If we have a set of reals, which I'm going to say this informally, I'm still thinking about limits here. If we have a set of reals which approach something, that thing that they approach is also a real number. It's not like you can't have a bunch of real numbers which approach something, but there's nothing there, like there's an empty space or something. What that thing they approach is also a real number. This statement actually is not true for rationals. Here's an example. If I have a set of reals which approach something, how about this? I'll just write like a little sequence of numbers. 3 is the first one, and then 3.1, and then 3.14, and then 3.141, and then 3.1415, etc. I'm trying to write sort of increasingly accurate decimal representations for pi, all right? Actually, I don't know any more numbers than that. I'm not a great wizard for memorizing digits of pi or anything else. Each one of them is a rational number because each one of them has a decimal that just ends after a few, after finally many, positions. But the thing that they approach is irrational, is pi, right? So each one is a rational number. I'll say in Q, this is how we write the set of rational numbers as a Q with the fancy bar. Q for quotient. You can't use R for rational because we use R for real. So you got to go for Q. Each one of these in Q, but they approach something that is not in Q, right? This is one way of saying that the rational numbers, that set Q, is not complete, because you can have a bunch of things in Q where they are actually getting close to, it seems like they're getting close to something, but actually the something they're getting close to is not part of their universe, right? It's not part of the set of Q. This is not possible in R. Of course, you will notice these things, they are each real numbers. And the thing that they approach is pi, which is also a real number. So R has no missing things in it. Everything that seems to be part of the number line actually is part of the number line. Unlike the rationals, which also live in a line, but there's a whole bunch of other stuff that's just not part of the set of rational numbers. All right, let's talk about some simple language again. I want to talk about sets being bounded and not bounded, which has a lot to do with what I just said, although it's not clear immediately what the relationship is. So simple definitions. We're going to say a set of real numbers. That symbol right there means a subset. A is a subset of the real numbers. So a set of real numbers is called bounded when, this is what you think it means. Bounded means that there's some number which is bigger than all the values in the set. The set doesn't like stretch all the way up to infinity. It eventually stops somewhere. So bounded means, the way I'm going to write that is, there's two kinds of bounded. We're going to talk about bounded above and also bounded below. So I'm going to say a set is bounded above. It means there's some number which is bigger than every element in that set. So I'm going to say it this way. When there exists a b in the real numbers such that a is less than or equal for all a in my set A. All right? This little st here means such that. So there exists b in the real numbers such that everything in my set is less than that number b. And this number b is called the upper bound for this set. It means that this is a single number which is bigger than everything in the set. So in this case, I'll say such a b is called an upper bound for the set A. All right? It is an upper bound. Actually, there will be many upper bounds. Like if b is an upper bound, b is bigger than everything in the set, then also like b plus 1 is also an upper bound. There's infinitely many upper bounds if there's any automatically. So I'll just say there will be many different upper bounds, right? If there's one, then automatically there are many. Yeah.
Can you just say backwards E before the B moves?
It means there is some b in the real numbers, such a less than b for all a. Sorry if this is not, my handwriting is not clear. This says such, I don't know what that looks like. It doesn't really look like such. Such a b is called an upper bound. Sorry about that. Suck a b, it looks like. That should be my YouTube channel name. Suck a b. Such a b, right? That point is called an upper bound. Okay? All right, and then we also have bounded below. So bounded above means that there's some single number which is bigger than everything in the set. You can also talk about bounded below, so I'm going to say that next. This is just what you think it is. A set A subset R is bounded below. When there is some particular number b, this time the b is going to be less than everything in the set. So such that b is less than or equal to a for all a in my set A. And this b is a lower bound. All right? That's what it means to be bounded below. There's some individual number that's smaller than everything in the set. All right? And a very important property that we're going to talk about, or important type of bound. Any questions about those so far? These, I think, are pretty ordinary concepts. Here is a big definition, which maybe you haven't heard this word before. If we have a set in R which is bounded above, like I said before, a set which is bounded above actually has many different upper bounds, actually infinitely many different upper bounds. If A is bounded above, then the least upper bound has a special name. Now, sometimes it's simply called the least upper bound. It is the smallest of all of the different upper bounds. The least upper bound is called this is a fancy word, supremum of A. And we write it this way, soup of A. It looks like sup, but it's soup, pronounced soup. I'm going to This is too, oh no. I'm trying to fix my S, and I wrecked it. The sup of A is the least upper bound. So a set which is bounded has many upper bounds. So you can think about what's the smallest of those upper bounds. That is what we call the least upper bound. More often we're going to call it the sup. And then we can do the same thing with the lower bounds. Although if you have lower bounds, there is no smallest of the lower bounds, but there is a biggest of the lower bounds because they live on the other side of the set. So if A is bounded below, I'm just going to write this and then we'll do some simple examples. The greatest lower bound is called, anyone want to guess what this one's called? Have you heard this before? The opposite of supremum? No, you wouldn't guess it. The infimum. The infimum of A. And we're going to write inf of A. All right? This is the supremum and the infimum. These are major concepts for this semester. The supremum is the least upper bound, and the infimum is the greatest lower bound. All right? Excellent. Let's just do a few simple examples. I give you a set, and you tell me what's the sup and the inf. Or you can tell me, first of all, is it bounded above? Is it bounded below? And then, furthermore, what is the sup and the inf? How about if my set is A equals the interval from 0 to infinity, like that. These are all going to be sets of real numbers. So this, I mean, the number 0 plus everything greater than this. First of all, is it bounded above? What do you say? No, it is not bounded above. Yeah.
The bracket means it's included.
Yes, that's right. So the bracket before the 0, the square bracket there, means I am including the number 0 in this set. This, when you have an infinity, you always use the curvy bracket because infinity by itself is not a number, so it doesn't make sense to include infinity as part of the set. Yeah, so this is not bounded above. That means in particular, so there is no sup, right? The sup is the least upper bound, but if it's not bounded at all, then there is no sup. That's why I said as part of this definition, if A is bounded above, then the least upper bound is called the sup. If A is not bounded, you don't even talk about the sup. Is it bounded below? Yes, I think it is. Can you give me an example of a number which is a lower bound? -1 is a lower bound, right? So it is bounded below. For example, -1 is a lower bound. Great. That means we can talk about the inf. What is the least? No, the inf means greatest lower bound. What do you say? It is 0. Yeah, maybe you might hesitate for yourself. Does 0 really count as lower bound? Because 0 is actually part of the set. It does count if you look carefully at the definition here. I said, come on now. Lower bound is right here. Is some number such that B is less than or equal to A. That means a number which is actually part of the set is allowed to be lower bound if really it's less than everything else. So, all right, this set, the inf of that is 0. Okay, great. How about, here's another example. I'll call it B this time. This one may be a little more interesting. Set 1 over n such that n is a natural number. So this symbol, this fancy n right there, means just the sort of whole counting numbers. Well, it's not 0 in this case. Let's just say 1, 2, 3, etc. Right? So this B, what I'm talking about, is just the set of all fractions which have numerator 1 and some whole number as the denominator. Yeah?
So the supremum and infimum always have to be within the set, right?
No, they don't actually. Yeah, actually in this example, one of them is not in the set. Let's try and think about this. If you were to, I could represent, this is a slightly weird set, I suppose. I could represent them like on a number line. This is 0, say 1, 2. The first number in this set would be 1 over n, where just start off with n equals 1. You get 1 over 1, which is 1. So the first point, I got colors here, right there, right? It's 1 over 1, which is 1. The next point would be 1 over 2, which is a half, which I could put here. The next point would be 1 over 3, which I could write around there somewhere. The next would be 1 over 4, which is like here, right? So these points, they do like that, right? Somebody tell me, is 0 part of this set? No, it's not, because 0 cannot be written as a fraction 1 over some whole number, right? So 0 is not in this set. Okay. Back to black. All right. Can we say, so just looking at the dots now, is B bounded above? Yes or no? Yes, it is. B is bounded above. For instance, 2 is greater than everything in the set B. All right. Can anybody say what is the sup of B? It would be the least of the upper bounds. What do you think? 1 is correct. Yeah. 1 is actually the largest element of the set, and we'll talk about this next time. I think if it's the largest element of the set, it automatically is equal to the sup. Is B bounded below? I already wrote it. I was going to say yes or no, but all right. It is bounded below. Can anybody tell me a lower bound for B? 0. Yeah, 0 is a lower bound. The number 0 is less than everything in the set there. Certainly something like -10 is a lower bound, right? It's definitely less than everything in the set there. So what is the inf of B? It is the greatest of the lower bounds. What do you think? Infinity? No. Yeah, it would be 0, right? In this case, 0 is a lower bound, and certainly anything bigger than 0 would not be a lower bound. If you think like, what about, 0.005? Is that a lower bound for B? It's not, because eventually when the n is big enough, you will have a fraction which is to the left of that value. So in this case, the inf of B is 0. So this demonstrates, I will just say, note that inf of A may not be an element of A. That is the case in this example. The inf here was 0, even though 0 is not part of the set. And same with sup. So sup of A may be or may not be in A. Right? The sup and the inf may not be in the set itself. All right, I guess it's time to go. We're going to talk some more next time about sups and infs. So I will see you then. Make a comment on our YouTube video.